In digital control systems technology, in the previous week, we have looked at feedback control systems and we briefly touched upon PID control. So, today we'll be exploring PID control a bit further, and we will also talk about a few other things relevant to using PID controllers in a application environment. And from a course perspective, PID controllers and building a feedback control system will be your main project assignment. So today's lesson will be an important one from that perspective as well. So when we think about feedback control systems, we said PID control is one of the important type of PID feedback control systems or ways we can build feedback control systems. So we identified that it is a three-part controller. It has three main components: a proportional component, an integral component, and a derivative component. So we will briefly look at what each of these things mean and why we use these within our controllers. So let's take, for example, let's take a simple example. We will say we have a vehicle that needs to move at a particular speed. So we are controlling the speed of the vehicle. So a vehicle is moving and we want to keep the speed of the vehicle at a particular speed. Say that is the speed that we want to keep for the vehicle. So now, from a controller perspective, let's say we are suddenly going in a downward slope. So the vehicle is now moving in a downward slope. So the speed of the vehicle is going to increase. So we may have to reduce the speed. So we may have to brake and reduce the speed. Or alternatively, say if we are climbing up a slope, then we may have to increase the speed. So we may have to increase the power that we are giving to the vehicle to keep up with the speed. So when we are going down the slope, the speed will automatically increase. So we will have to reduce the speed. If we are going upwards, the speed will automatically reduce. So we will have to increase the speed. So that is the change that we will have to make. So now let's say when we are going down, our speed became 60 now. So our speed is now 60. But we want to keep it at 50. So now the difference here is 10. So we want to compensate this 10 difference in some manner. So one of the quickest way we can do is doing a proportional control with proportional to the error value. So this is the error value. So we want to do some control proportional to the error. So if we are 10 above the speed, we want to apply the brake more. So if the speed is about 20, so now we want to apply more brake. If it is 30, we would want to apply the brake even more. But if the error is like 5, the amount of brake will be less than what we need when we are at 10. So you can see when the error is more, when the difference is more, we will have to fix more. The fix that is needed is also more. So that is the main idea behind proportional control. It is proportional to the error value. So if the error value is high, the amount of force, for example, we apply is also high. So that is the basic idea behind proportional value. So we are applying a correction that is proportional to the error value. So proportional to the error value. If the error is higher, the proportional application will also be higher. Then that is perfectly all right. So we have the proportional component that we have there, and we are applying that. So that is the proportional gain. But what would happen is, say I apply the brake when the difference is, or the error is 20 kilometers per hour. So I apply a particular amount of brake because 20 is very high, I will apply that. But when the difference is becoming lower and lower, when it is say 1, the amount of brake I am applying will also be very low. And that low amount of brake may not be sufficient, and the car may still keep on reducing. So the amount of effect that is available at the very lowest proportion may not be significant, and when it is below that, like 0.5 and so on, it is again less effective. So when we go below, in terms of when we have a higher proportion of error, then the effectiveness of proportional gain is pretty good. But when we are going further down and down, this becomes less and less effective. If the change is very small, or the error is very small, the effectiveness of the small and the error is also, the proportional application is also very small and not very significant. So at that point is where we are going to use what is called integral component, or the integral gain. So you may remember integration from mathematics. So what is the basic idea of integration? So if we normally plot a change in the graph, so if something is changing in the graph, what do we mean by integration at a particular point is, we add the values, all the values up to that point. So technically the area that is covered by this part of the graph. So we add the value here, here, here. We continuously read the values, and if we sum them up, all of them together, that is what we mean by integration. So when we look at integration, what would happen is, say initially it was 20, then it became 10, it became 5, 1. So as we go along, the proportional component is also reducing significantly. So that is the problem that we are facing. But if we think about the integration component, it will keep on adding. It will be like 20, then it is 30, then 35, then 36. So it is continuously increasing. So what we would have is, even towards the end, we will have a significantly higher value that can significantly apply to the change that is needed. So the proportional to the error will reduce, but the integration of the error values will increase. So we can use the integration value towards the end, or when we are closer to having less amount of error. So if when the error is lower, proportional component is not going to be the significant one, because it is almost insignificant, the proportional component, but the integration component will become the important one that is still going to control and stop the vehicle or bring the speed of the vehicle as we expect. Because otherwise what would happen is, if we only go by the proportional value, here the brake will not be applied significantly, so the reduction of speed will not be achieved, whereas with integration we can do that. But between proportional and integration component, we have one issue that we don't achieve so far. That is how quickly the system can adapt to a change. So for example, if we suddenly fall into a slope, so suddenly we go into a slope, the vehicle is going down in a slope, the speed is going to increase suddenly. So we have to quickly adjust to that. But whereas the proportional component and the integration component may not react very quickly. So that is where we use the derivative component. So again, if you recall derivation from your mathematics, the idea of derivation is the rate of change. So normally we get the tangent of the graph, and that is the rate of change. So how quickly it has changed. So with derivation, we not only we don't see the integration part or the proportional part, we see the change, how quickly something is changing. If it is changing quickly, then the effect will also be applied quickly. If it is changing slowly, the effect will also be applied slowly. So for example, if you suddenly go into a slope, then the derivative will be higher, so it will apply a higher brake quickly. So first it will react quickly, so most of the things are fixed, so the sudden changes are accounted for. Then after that, if the changes are slower, then the derivative component will not be significantly important there. So that is the main aspect of these three components: the proportional component, the integral component, and the derivative component. Each of these components have their own purpose, have separate reasons as to why we use them. So there's actually a good example. I would suggest that you go and try out in this particular video, and then there's also another online tool where you can try out different proportional, integral, and derivative values and try out how things are impacting on a system. But in summary, what we get is, with proportional, we get the main error. It is proportional to the error. So that is the one that we are going to get as the main part of controller. So the control output is going to be mainly dependent on the proportionality with the error. But with integration, what we achieve is, we are trying to achieve what is called steady state error. So the idea behind steady state error is, what we may end up when we are using, say, only proportional control is, say, if we want to achieve 50, as the target speed that we want to achieve, what we may do is, we may say, if we reach 60, we may try to bring it down, but we are not able to stop here. We may go down and we will oscillate around here. So we are not able to achieve the results that we need to achieve. So that is what we achieve with the integral component. That is, it produces the steady state error. So it may produce a steady state error. Whereas the derivative component, it is mainly about providing a rapid system response. So it is about achieving a rapid system response. So it can react to the system, react to the changes in a very rapid manner, in a quick manner. So the problem with proportional component is the instability. So it is going to oscillate. So the instability is the problem with the proportional component. Whereas the integral component, it is going to be slow to respond, because it will be accumulate. So it is integrating. So initially it is a lower value. The value is only increasing over time. So the integral component increases over time because it is accumulating all the values so far. So initially it will be very slow to respond to changes. So the derivative component is the one that is going to fix that, and that may also have certain issues like noise and non-zero offset errors, which we can look at later as well. There's another online video I will strongly suggest that you refer to get a better understanding of PID controls. The things that I have explained so far are also explained here again, and so that would be useful to understanding what are PID controls and so on. Then with PID controls, one of the other things that we can do is we can combine them and use them. So instead of using only the proportional component, we may use, for example, the proportional and integral component, or the proportional and the derivative component, or all three of them. So in our feedback loop that we have, what we can do is we can say, for example, we can, this is the standard feedback loop. We have the plant is there, the controller is here, then there are some sensors, they are sensing the error, and then the error is fed back into the controller. Then the error can be multiplied by our proportional component, or the integral component, or the derivative component to get the output variable, the control variable to the plant. So this error can be either, we can take the proportional component of the error, or we can take the proportional and the integral component of the error, or we can take the derivative component of the error, or we can take a combination of those. So we may have P controllers, PI controllers, PD controllers, and PID controllers, which we are mainly interested in. So when we look at each of these examples separately, each of these cases separately, particularly when we think about proportional controllers, what we have with proportional controllers is we are multiplying the proportional value, multiplying the error value, and we are taking a direct proportion of the error. So that is what going to be the control output. That is what we are going to apply as a brake. Say if the error is 20 kilometers, we will apply 20 times a particular variable of the brake, so a particular force or whatever. If the error is lower, now the error is 10, so now the multiplication is by 10. So that is the proportional control. And from an implementation point of view, it is one of the simplest one to implement, because we just take the error value, we multiply that, and we apply the effect. So it can be very easily done, and without the need for a lot of complex computation, because it is just a multiplication with the proportionality of the error. The disadvantages, the main disadvantage with the proportional control approach is the oscillations that we would get with using proportional control. So for example, what we may get is one of the examples that we discussed last time is about, say, there's a wall and we want to walk towards the wall and stop there. So that a vehicle needs to go towards the wall and stop there. So now it is at 10 meters. So it will go at a particular speed and it will move towards that. But when it is closer to here, we want to stop at the point, but it is at 1 meter. So the speed is again, say, 1 meter per hour. So it is never going to reach 0, even a little, the 0.1, it is still a positive value and is still going to move. And by the nature of sort of physics and how things work, it cannot suddenly stop at that point, and it may go past this point and stop after a bit. So then if it stops missing the point, then it has to come back again. So it will try to reverse. Again, it will use proportional control. Again, it will come back, maybe not stopping there, coming a bit further. So then it will have to move back and forth. So that is the oscillation of error that we would find in proportional control. So it will go back and forth between the targeted value. So that is the one that we would try to avoid with proportional control, or that is what we would encounter with proportional control, and we want to avoid that using other approaches. But the reality is the proportional control is still the useful one, because the proportional control will give you the largest difference that you need to work particularly. So if the difference is larger, it will give the largest effect at the beginning itself. So you would always use the proportional control. You will not use only the integral part. You will always use the proportional and maybe the integral part or the derivative part along with that. So when we take the integral part along with that, this is mainly about how we can dampen the effect over time. So if we start applying the brake over time, the effect, so if we say the speed is reducing, the amount of brake we are applying, we are going to reduce the amount of brake that we are applying. So that will lead to a point where the vehicle is never stopping. So with integration, what we are doing is the integral value is going to increase and increase and increase. So then over time, even if the proportional value is reducing, the proportional difference is reducing, the integral value is now increasing. So the impact from the integral component will be now higher, and that will bring down the component or bring down the system to a zero value. So it is mainly to bring the value back to zero, bring the steady state error value back to zero. So it is a way to bring the controller to the desired point rather than having oscillations or never stopping and sort of slowly moving kind of a situations. Avoiding that is the main aspect of using a integral controller. But one of the main disadvantages with integral controller is now we need some more computational capabilities, because we have to do integration, and as you know, integration is adding the values over a period of time. So we have to have some memory, we have to keep track of things, keep track of time and these values, and we have to produce the integral value every period of time and then apply that. So proportional component was much easier, just a multiplication of the error, whereas the integral component we have to do a bit more work, bit more computational requirements are necessary. So that is something that we have to consider. So proportional component is much easier to implement, but it can lead to some errors, whereas integral component can be useful in eliminating those errors, but we may need some additional computational capabilities. Another problem that we get with the proportional component is what is called maximum overshoot, and also the ability for the system to respond quickly. So for example, we are going at a slow speed and we are suddenly increasing the speed, or the speed increased suddenly because of the external disturbances. Somebody pushes the vehicle or something, the thing moved quickly, so we have to stop it quickly. Because the change was sudden, the integral component is not going to amount quickly, it is not going to react quickly. But with the derivative component, what we are getting is the rate of change. If something suddenly changes, we are mainly calculating the rate of change. So that is the tangent value in the graph, for example, if you think about derivation. So the rate of change is what we are taking, and if it is a quick change, we will apply a quick brake. Say for example, if we are suddenly dropping into a slope, we will apply the brake quickly. So then we are slowed down significantly, and then we can manage using the other component. So the derivative component is all about the sudden change and applying the effect for those sudden changes. So it is mainly about the fast response that we can get. But we still have this one would still have the issue of, say, steady state errors. Or if you are only using the PID controller, we will still have the steady state error issue. And if there are sort of noises, if there are certain smaller external changes also, the derivative controller may try to amount to that, try to affect the change based on the smaller changes. So that is also an issue that we may have. But it solves a different problem than the integral component. So when considering all these components, the proportional, integral and derivative component, what we would identify is each of them have slight disadvantages, but when we combine all of them, most of those disadvantages are addressed by one of the other components. So when we combine all PID components, proportional, integral and derivative components, now we don't have the steady state error problem, and also we reduce the maximum overshoot issue. So those are some advantages. But the disadvantage, one of the main disadvantages is now we need more computational capabilities. It becomes much more complex to implement. The implementation becomes much difficult. And also, one of the other issues that we will find is identifying the K values. So if you recall the main PID controller equation, we always had a constant value multiplying the error value. Then there was a constant value multiplying the integration. Then there was a constant value multiplying the derivation. So all of these, we had these K values. So that identifying what is the suitable K value is what we mean by tuning or getting the proper expected outcome, and that is a challenge here. For example, the difference of speed is say 20 kilometers per hour, that is the error value. That doesn't mean we are always multiplying, or the input that we are giving to the plant needs to be 20. It may have to be an RPM value, so we may have to multiply by the 200 or whatever. So we may have to give the input multiplied by some constant, so that is suitable for that particular system. So identifying that K value is the main challenge in using this PID controllers, and identifying them appropriately so that one component is not significantly impacting more. We need to find the balance. So K value should be impacting as expected, I should be impacting as expected, and D should be impacting as expected. So finding that balance is the main challenge that we have when we are considering the PID controllers and tuning the PID controllers. So when considering the PID controllers, one of the main things that you will have to figure out and you will have to configure is the K value. So when you are implementing these as part of your projects, the basic PID controller, the functions, the equations, the algorithms are fairly same for all use cases because it's the same thing. But the K values are the ones that you will have to figure out depending on what you need to do, what you expect your system to do. You will have to tune, you have to figure out, you will have to find out the particular suitable K values for your use case. So that is something that you will have to implement in your project situation. So this table summarizes some of the changes that can happen when you are using different K values, what you can achieve by using K values, or what you can do by increasing or decreasing the K values. And this is something that would be very much relevant when you are building your projects. So when we talk about tuning controllers, when we talk about tuning PID controllers, what we mean by tuning controllers is particularly identifying these K values, particularly identifying these constant values suitable for the PID controller, identifying those K values and identifying them so that there are no system oscillations, or we are reducing the system oscillations, we are getting good response times, we are reducing the steady state errors, and we are achieving stability. So that is the main requirement that we would have when we are implementing, or when we are implementing a controller and when we are doing the tuning of controllers. So achieving that steady state, achieving the stability would be the main target of tuning controllers. And there are a number of ways that we can do this. We can do this manually, but it can be a lot of time consuming thing, because we can set the p value for something and we can slowly go into uh, the other type of values, and we can slowly see how we can change them. So that is possible, but that type of manual change may be very time consuming and also may not be accurate, and can be very difficult when we are considering sort of larger systems. There are a number of automatic controlling mechanisms, tools, and such that uh, tuning controllers is not a key part of the theoretical component of this course, but you may have to do that when you're actually implementing your project. So you may look into that from that perspective. And there are a number of other tools and mechanisms to do them in an automated manner as well. So, if you think about a sort of manual or a simpler approach to tuning controllers, uh, what we can do is we can set the p value, say for example, to a smaller value. So we would start with a smaller p value, and we can set d and I for 0, and then we can increase d value until we are getting oscillation, and then we reduce that, and then we can increase I, and then we can increase p, and then again when it is overshooting, when we can bring that back, and then we can bring in I, and then when it is overshooting, then we can bring that back. So again we are going one after the other, and we are changing these k values, increasing. When it is a problematic thing, we'll bring it down. So likewise we go through this loop, and at some point we can achieve a fairly stable system. But this is a fairly heuristic sort of fairly manual approach that we can take. There are a number of other mechanisms, other methods for tuning PID controllers. We are not going to go detailed discussions into these, but you may refer to some of these when you are implementing a projects. You may consider using some of these approaches. You may read about these approaches, and if suitable, you may use them. Another sort of approach is again we are setting, similar to the previous one, we are setting d and I to 0. We increase p, increase I, increase d. Again we are going through this iteration in a slightly different order, but basically we are sticking to the same approach in a manual tuning mechanism. But when we consider sort of modern control systems, industrial systems, manual tuning is not what we are going to use. We are going to largely depend on sort of software-based mechanisms, sort of automated tuning software. So it may measure the effects, and based on the feedback nature of these systems, they can identify. So these mechanisms can be these sort of heuristic approaches can be done in a more organized manner, in a more programmed manner, and they can find a better tuning for a particular system using these approaches. So again, there are a number of systems that can be used for these, number of software systems. It is not in the scope of this course, but you may get to use these things if you're implementing such systems in a larger environment. So, as I said, PID controllers is a significant part of this course. Particularly, that is something that is essential for building your class project, building a project for this course. So, there are a number of additional resources that I'll be sharing that you can refer to, online videos and such, to get a better understanding of PID controllers and feedback control systems and how to build them. Using different tool sets, and then you may get a better understanding and how to tuning them and so on. particularly that would be essential and necessary when you are thinking about building your project. So in addition to PID controllers, we said there are some other type of feedback control systems that were used or that are there. And one of the examples that we mentioned is what is called the lead lag compensator. So lead lag compensators are not the main types of controllers we use anymore, because PID controllers are the ones that are pretty much used by everyone in most use cases. But lead lag compensators were particularly prominent in sort of analog systems, particularly before we had many sort of digital control systems. Lead lag compensators were the type of control systems because they were based on the nature of frequency and phase nature of electric signals, and that is what they were used. But they were, when compared to PID control system, there are many disadvantages, many difficulties in building them, many disadvantages in terms of the accuracy of the systems, the outcomes that we can get, and also the ability to modify and change these systems. So for that reason, lead lag compensators are no longer commonly used, but at least you need to be aware that such feedback control systems also exist. So you have a broader understanding of feedback control systems. But other than that, we'll be mainly focusing on PID controllers in this course. So the idea behind lead lag controllers, for example, lead is about so the leading the phase. The phase is about the cycle of the signal. So here this is leading the phase, and alternatively lag is about, and this one is lagging the phase. So, and based on those difference, we can enact some changes, enact some controllers. And I would highly suggest you refer to this video to get a better understanding of lead lag compensators. So the main thing that we discussed today is PID controllers and how we can implement each of these components, and what are the importance of each of these components, and why we use each of these components, and then the importance of tuning the constant value, the K value, and how we can change that to achieve a combination of a PID control. And we briefly touched upon lead lag compensator, but as I said, PID controller is the main focus of this course, and that is what we would be focusing in terms of your project as well. So that's all for the main discussion points for the day. And if you have any questions about these, you may ask now, or you may post them later as well. And we could also discuss about projects after this. If you have any questions about the project, we can discuss about those as well. So other than that, thank you.